In the previous two chapters, we examined reactions of carbonyl compounds that involved reaction of the carbonyl group. Now we are going to look at a little bit different type of reactions. We are going to look at reactions next to the carbonyl group. And those reactions are substitutions alpha to carbonyl group. In this first part of the chapter, in the introductory part, we are going to examine addition versus substitution, what are enolate ions, and finally we are going to look at one specific type of reaction, halogenation of carbonyl compounds. First, just to remind you a little bit about nomenclature. So according to trivial nomenclature, carbon atoms next to the functional group are labeled as alpha carbon atoms. In this case, functional group is carbonyl group, so carbon atoms next to the carbonyl carbon are alpha carbons. Atoms next to alpha are beta, and then next to beta gamma, and so on. In each case, we could have more than one alpha, beta, gamma, and so on atoms. If chain is long, then without counting the number of atoms and figuring out which letter of Greek alphabet would be assigned to that carbon, we simply, for a long chain, indicate last atom in a chain as omega, and next to last would be omega minus 1. You already are familiar with electronic structure of carbonyl compounds. That oxygen atom of the carbonyl group exhibits rather strong negative inductive and negative resonance effect, and that makes carbonyl carbon electron deficient. So carbonyl carbon in ordinary carbonyl compounds such as aldehydes and ketones exhibits high degree of electron deficiency. That in turn makes it rather electronegative, and it will withdraw electron pairs it's sharing with neighboring atoms, including neighboring carbon, like alpha carbon, and that in turn makes alpha carbon electron deficient. So this is simply an effect that spreads through sigma bonds, inductive effect of the oxygen atom, that in turn makes alpha carbon electron deficient. Alpha carbon, being electron deficient, is more electronegative, and that causes carbon-hydrogen bond to be polarized. And as bond is polarized, carbon is partially negative end of the dipole, hydrogen partially positive. That means that these hydrogens become acidic, to some extent acidic. And as they are acidic, they could be removed by a base. Alpha carbon usually has more than one hydrogen, and so those are all considered to be acidic hydrogens. But regardless of how many hydrogens there are on alpha carbon or alpha carbons, only one single hydrogen can be removed by a base. So overall, now we can see that carbonyl compounds can undergo two types of reactions. Nucleophile will react with carbonyl carbon. Nucleophile will donate its free electron pair to carbonyl carbon to form carbon nucleophile bond, while base will deprotonate alpha carbon. So electron pair from a base will form bond to proton, and that will deprotonate alpha carbon. And here are two types of reactions. So nucleophile, at least in the first step of the reaction mechanism, whatever the carbonyl compound is that reacts, in the first step of reaction mechanism, nucleophile donates free electron pair to carbonyl carbon to form tetrahedral intermediate, and then reaction goes from there. On the other hand, base deprotonates alpha carbon, and that results in formation of enolate anion. Enolate anion is a nucleophile and reacts with an electrophile to give the final product. So overall reaction is replacement of proton by an electrophile, and that means a substitution. And since it occurs on alpha carbon, it's called alpha substitution. So one question is just how acidic are those alpha hydrogens? So and here we are going to examine some common compounds. First, alkanes, of course, have carbon-hydrogen bond, and they're completely non-acidic. Their pKa has been estimated at about 50. And it's only been estimated because in order to determine pKa value of a particular carbon-hydrogen bond or particular bonds to hydrogen, we need to establish acid-base equilibrium and find out where that equilibrium is. In this case, we actually really cannot, we don't have any base that could deprotonate compounds such as ethane, and we cannot establish equilibrium, so we are estimating pKa at 50, which means that really it cannot be deprotonated. So it's not really acidic. Now, when we look at typical ketone, its pKa is 18 to 20, and that depends on nature of substituents R1 and R2. Just for the reference, pKa of water is 15.7, and of alcohols, depending on structure of alcohols, about 15.5 to 16. So this is considerably less acidic than water or alcohols. Aldehydes are considerably more acidic than ketones. Note that pKa value is logarithmic scale. So depending on the nature of the substituent R, pKa value of an aldehyde is between 15.5 and 17. Esters have an electron-donating oxygen substituent that considerably reduces electron deficiency of carbonyl carbon, as we have seen in previous chapters, and also reduces acidity of alpha hydrogen. So pKa value is considerably higher. It's around 25. So it takes considerably stronger base to deprotonate an ester. Amides are somewhat unique, and amides don't usually undergo alpha substitution because they're not easy to deprotonate. Nitrogen is very good electron pair donor. It compensates to a large extent electron deficiency of carbonyl carbon, and for that reason alpha hydrogens have very low acidity. It has been estimated at about 30. If amide is primary or secondary, it will have hydrogen attached to nitrogen, and that's the one that is acidic. That's the one that can be deprotonated. And we have seen one example in Gabriel's synthesis of primary amines in the previous chapter. So pKa of that hydrogen is typically around 17. If amide is tertiary, then we are only left with alpha carbon and its hydrogens, and with pKa of around 30, that's very difficult to deprotonate. Not impossible, but not usually carried out. It could be done, but usually that reaction is not carried out. And we can compare that with pKa of amines, which is about 35, so not that different. It is noticeably acidic. Amide is noticeably more acidic compared to amine, but still very low acidity. Effects of carbonyl group on acidity of alpha carbon are additive, which means that two carbonyl groups will make alpha carbon much more acidic. So dialdehyde has pKa of around 5. That's actually very acidic, and it's about as acidic as carboxylic acids. These compounds are very easily deprotonated by using a base such as hydroxide or alkoxide. Diketones have pKa of around 9, so not as acidic as dialdehydes, but still very acidic, and they could be also easily deprotonated. Then we have an example of ketoester. This will be beta ketoester. pKa around 11. So we can see as groups become less acidic or less electron withdrawing, then acidity of alpha carbons decreases. But still it's pretty high. All these compounds can be very easily deprotonated by an alkoxide or hydroxide. And the same is the case with diester. While ester itself has relatively low acidity, pKa of 25. Beta diester, so two ester groups are in better position to each other. Both are attached to alpha carbon. Has typical pKa of around 13. And that's quite acidic. Again, if we use alkoxide that corresponds to the leaving group of the ester, it will easily deprotonate this ester, and deprotonation will be quantitative. We have just examined different acidity of different types of carbonyl compounds, different classes of carbonyl compounds. So some are more acidic than the others. In general, acidity of any acid depends on stability of its conjugate base. So upon deprotonation, an acid loses proton to give conjugate base. The more stable the conjugate base is, the stronger the acid. Different classes of different carbonyl compounds give different, of course, conjugate bases, and based on their stability, they have different acidities. So when we consider typical carbonyl compound, a ketone, here is acidic proton circled in red, so it's removed by a base to give enolate anion as the conjugate base. So enolate anion is stabilized through resonance, as you can see from these two structures. So electron delocalization or resonance makes enolate anion stable, and that's what makes resulting ketone acidic. The more stable enolate anion is, the stronger the acid. we can compare ketones with esters. So esters, upon deprotonation, give this enolate anion shown on the left. This enolate anion has same two resonance structures, so one on the left and in the middle, that we have seen in the case of ketones, enolate anions generated from ketones. But there is third resonance structure, shown here by curved arrows, and then resulting structure on the right, that is not present in case of ketones. And that resonance structure actually destabilizes enolate anion, because electron pair donation from oxygen, as shown here, pushes electron density back on the carbon, on the carbanion, and that's destabilizing. So this enolate anion is less stable compared to enolate anion generated from a ketone. For that reason, esters will be weaker acids compared to ketones. And not only carbonyl compounds are acidic, but any species that has electron withdrawing group that can stabilize resulting carbanion is going to be acidic. For example, nitro group is known to be highly electron withdrawing. As a result, nitroalkanes are acidic and behave in a manner similar to carbonyl compounds in generating carbanions. So nitro compounds are easily deprotonated on carbon attached to nitro group to give corresponding carbanion, and resulting carbanion, as you can see from these two structures, is stabilized through resonance. In fact, degree of resonance stabilization is rather high, and nitroalkanes have very low pKa. They are very acidic. They are actually considerably more acidic than aldehydes. So pKa of nitroethane is 8.6. Now, another concept we need to examine that is very important for explaining reactivity of carbonyl compounds, of substitution of carbonyl compounds, is Keto-Enol Tautomerism. Tautomers are isomers that exist in two forms, and those two forms differ in position of double bond and hydrogen atom. In case of carbonyl compounds, those two forms are called keto and enol forms. You are familiar with carbonyl compounds and mainly their keto form. So most of the carbonyl compounds are more stable in keto form than enol form. But there are a few exceptions, and you may not have thought about that, but phenol actually is an enol form of keto form of 2,4-cyclohexadienon. So enol would be, for enol form would be phenol. And in this case, because enol form is stabilized through aromatic ring, it's actually the only form that is present at equilibrium. We don't have any keto form. Position of keto-enol equilibrium, of course, depends on relative stability of two forms, and that depends in part on nature of substituents. So typical ketone mainly exists, as shown here for acetone, in keto form. Enol form is present only in trace amount. In cyclic compounds, actually enol form is present in larger amount, and that's because double bond inside the ring is more stable compared to double bond outside the ring. And so we have larger amount of enol form. And finally, some other outside factors, such as ability to form intramolecular hydrogen bond, will favor formation of larger amount of enol tautomer, so as in this case. So for example, beta keto esters will have considerable amount of enol form. In this particular case, 14% of enol form and 86% of keto form. So enol form is very important when it comes to reactivity, because that's often the form from which carbonyl compound reacts. So keto form and enol form are interconvertible into each other, but only in the presence of an acid or a base catalyst. Under basic conditions, two forms interconvert by first deprotonation of the alpha carbon to give corresponding enolate anion. And that enolate anion is then protonated to give enol form. All of these steps are reversible, and of course, reverse step starting from enol form will give keto form. Under acidic conditions, first carbonyl oxygen is protonated to give corresponding oxonium ion, and then that oxonium ion is deprotonated at alpha position, accompanied by movement of pi electrons to give enol form. Again, as in case of base catalyzed reaction, all the steps are reversible, and starting with enol form, these steps in reverse will give keto form. So keto and enol forms are important, as already mentioned, because those are forms from which carbonyl compounds react to give substitution alpha to carbonyl. Under acidic conditions, it's the enol form that is the reactive form. So first, carbonyl oxygen is protonated to give oxonium ion, and then deprotonated to give enol. We have seen that a minute ago. Now, from this form, enol reacts with an electrophile. And it reacts in such a way that carbon-carbon pi electron pair flows to form carbon electrophile bond, and it's assisted in doing so by free electron pair from the oxygen, which flows to form carbon-oxygen pi bond. The resulting species is oxonium ion. Substitute oxonium ion where electrophile has replaced original proton. Final step is deprotonation, which regenerates acid catalyst, shown here in amber, and we isolate substitute compound. Under basic conditions, first step is deprotonation of carbonyl compound by a base. That gives enolate anion. Here are two resonance structures. Typically, we use resonance structure on the left, and simply what we call that push electrons. We use curved arrows starting at free electron pair on the carbon, on carb anion, and simply push that free electron pair to electrophile to form carbon electrophile bond. Here I have shown it on the right, just to show movement of electrons, that we can do that from the other resonance form of enolate anion. So a free electron pair from oxygen flows to form carbon-oxygen pi bond, and that forces carbon-carbon pi electron pair to flow towards electrophile to form carbon electrophile bond, and that gives the substitute product. And now we're going to look at specific reaction, halogenation alpha to carbonyl group. That means replacement of alpha hydrogen with one of the halogen atoms. Those could be chlorine, bromine, or iodine. Substitution with fluorine does not work, as you might expect. First, we are going to examine halogenation under acidic conditions. Under acidic conditions, only monohalogenation occurs. That means only one of the alpha hydrogens can be substituted, and then reaction stops. That's because the product is much less reactive compared to starting material. So the product, alpha halo carbonyl compound, is much less reactive compared to starting carbonyl compound, and it won't react again. Byproduct is molecule of the corresponding hydrohalic acid. And so here are several examples. Reaction with chlorine in presence of an acid like hydrochloric acid. In case of bromine, we would use hydrobromic acid as the acid. And in case of iodine, we would use hydroiodic acid. Of course, in each of these cases, of these three examples, we could have exchanged, switched reagents and get correspondingly different products. For example, here we could have used bromine, and product would have been 2-bromocyclohexanon, or chlorine, 2-chlorocyclohexanon, and so on. Reaction mechanism involves initial formation of the enol. So from a carbonyl compound, under acidic conditions, first carbonyl oxygen is protonated to give oxonium ion, and then deprotonation at alpha carbon gives the corresponding enol. That enol now reacts with halogen, in this case bromine. So electron pair from oxygen goes, free electron pair forms double bond, carbon-oxygen double bond, or reforms it, and that causes carbon-carbon pi electron pair to form bond with bromine. In turn, that causes bromine-bromine bond to break. The result is formation of oxonium ion, and that oxonium ion is deprotonated by bromide anion that was just released in the previous step, and that gives the final product, or products. Final product, organic product, desired product is 2-bromocyclohexanon, and byproduct is molecule of hydrogen bromide. So reaction stops here because 2-bromocyclohexanon is unreactive and won't react any further. The same reaction, halogenation alpha to carbonyl group, can be carried out under basic conditions. But under basic conditions, it follows a little bit different pathway. In that reaction is exhaustive substitution, which means that all of the alpha hydrogens are replaced by halogens. The reason for it is that upon substitution of hydrogen with a halogen, the resulting product is more reactive than the starting material, and next step, next substitution, second substitution proceeds even faster, and third even faster than the second, and so on if there are more hydrogens. The reaction was used a lot in the past as diagnostic reaction, because if there is methyl group attached to carbonyl, so if compound is methyl ketone or methyl aldehyde, acetaldehyde, then exhaustive halogenation would result in what is called haloform reaction. So product would be corresponding haloform compound. That would be chloroform, bromoform, or iodoform. And in particular, useful reaction was iodoform reaction, because iodoform as a compound that's CHI3 is yellow solid. So formation of yellow precipitate was considered to be diagnostic reaction for presence of methyl group attached to carbonyl. Of course, those reactions are not used anymore. Now we have spectroscopy to determine structure of an organic compound. But still, this reaction has historic importance and is studied a lot. Chloroform has formula of CHCl3 and bromoform CHBr3. And here is the reaction mechanism. So, reaction starts by deprotonation of the carbonyl compound to give corresponding enolate anion, and then that enolate anion reacts with, in this case, iodine. We are going to look at iodoform reaction, one that was the most commonly carried out. So, carbanion forms bond to iodine, and that results in breaking of iodine-iodine bond. Resulting product is alpha iodo-ketone. So, ketone substitute alpha position by iodine. And now that alpha carbon actually has two electron withdrawing substituents, carbonyl group and halogen atom, iodine. So it's more reactive compared to original alpha carbon. And reaction with base is even more facile. So second deprotonation occurs to give another carbanion, enolate anion, which reacts with second molecule of iodine. This second molecule of iodine now again iodonates alpha carbon and releases second molecule of iodide anion, which is byproduct and is of no interest to us. Now this compound is diiodo derivative, so it is alpha-alpha diiodo ketone. It's very acidic because alpha carbon is now activated by 3 electron withdrawing groups, carbonyl group and 2 iodine atoms. So removal of the remaining hydrogen is very easy, and base removes that third hydrogen to give the final possible enolate anion, and that enolate anion reacts with third molecule of iodine. Again, carbon-iodine bond is formed and iodine-iodine bond is broken. And now we have triiodo derivative. Triiodo derivative reacts with hydroxide. Now, hydroxide can act either as a base or as a nucleophile. Since there are no more acidic protons, hydroxide can no longer act as a base. And now it acts as a typical nucleophile in a manner that you have seen before in the previous chapters. So as a nucleophile, it adds to carbonyl carbon to give tetrahedral intermediate shown at the bottom. That tetrahedral intermediate will follow pathway that we have seen before. Carbon-oxygen double bond will reform, and that will be accompanied with breaking of the weakest bond to carbon. Typically, carbon-carbon bond is strong, and carbon atom is not a living group. But in this case, we have carbon atom attached to 3 electron withdrawing substituents, 3 iodine atoms. And that makes this carbon atom a good living group. The result is that that carbon-carbon bond will break. And so as carbon-oxygen double bond is reformed, bond to Ci3 is broken. That results in formation of carboxylic acid and carbanion. Carbanion is strong base, and we have acid present in the reaction mixture, so there is going to be proton transfer between acid and carbanion, and we end up with final products. final products are carboxylate anion and molecule of iodoform. Iodoform precipitates as yellow solid, and that's an indication that methyl group was attached to carbonyl group. So that will be positive iodoform test. If ketone does not have methyl group, let's say that's cyclopentanone, cyclohexanone, or let's say 3-hexanone, then this reaction would be negative. Iodoform would not form. Only alpha hydrogens would replace. So in each of those cases, each of those examples I mentioned, 4 hydrogens would be replaced, 2 on each side of the carbonyl group, but there would be no formation of iodoform, and so iodoform reaction would have been negative. Finally, another application of this alpha substitution is in preparation of alpha halo acids. So carboxylic acids substitute in alpha position by halogen, chlorine, bromine, or iodine, usually bromine, and that's called Hell-Volhard-Zelinski reaction. That reaction involves 2 steps. First step is reaction with phosphorus tribromide, or phosphorus tribromide is prepared in situ, that means in the reaction mixture, by mixing red phosphorus and liquid bromine in the appropriate stoichiometric amount. And then in the second step, we carry out hydrolysis with water. The resulting product is alpha bromo carboxylic acid. So the reaction occurs first by reaction of carboxylic acid with phosphorus tribromide to give acyl bromide. We have covered that actually at the end of previous chapter, preparation of acyl halides. So first step is preparation of acyl bromide, and then that acyl bromide reacts in the form of enolate anion with bromine. This is typical reaction of enolate anion. So carbon-oxygen double bond is reformed, and carbon-carbon pi electron pair forms bond to bromine. That results in breaking of bromine-bromine bond. The result is formation of the corresponding oxonium ion, which is deprotonated by bromide anion released in the previous step. And we end up with this as a product. We have acyl bromide that is substituted in alpha position by bromine. Now, when we add water, water will hydrolyze acyl bromide to corresponding carboxylic acid, and product is alpha bromo carboxylic acid. This completes first part of chapter on alpha substitution of carbonyl compounds, and then next we are going to continue study of alpha substitution by examining aldol condensation and related reactions.